Welcome to your podcast for Lesson 41, Tension. After watching the podcast, you should be able to define tension and find the tension in a string, rope, or cord within a system of objects. For the warm-up, I want you to picture two teams playing tug of war. Okay? So we'll just draw these teams as individual people. Okay? And we know that they are going to be pulling on this rope that's between them in the tug of war with a force of 500 newtons. And so we know that as they pull, they're going to be pulling in opposite directions of each other in an effort to win. And so think about what is the tension going to be in this rope. If I put a little spring scale here that would measure that tension. A common misconception that people will have with this question is that if one team is pulling one direction with a force of 500 newtons and the other team is pulling in the other direction with 500 newtons, that these two forces are equal in magnitude in opposite directions, so the answer would overall work out to be 0. But if you were the rope and you were being pulled on in each direction, for example, if you put your arms up and had somebody yanking on each one of your arms, you would know that that definitely is not the answer. Other people will look at this and say, wow, if that was my arms and somebody was pulling with 500 newtons in each direction, then it would be 1,000 newtons. I'd add them together. And it turns out that that is also not correct. And what's going to help us answer this question is if we look at each of these teams as different objects within the system. Or in other words, think of it this way. If I had a wall with a rope attached to it, and I pulled that rope with 500 newtons of force, we know that that rope would be pulling back with the exact same force, 500 newtons. And so this is the exact same thing as two different sets of people pulling on it. So the correct answer is 500 newtons, and we'll see a diagram of this in the next couple slides. All right, so when you see tension, don't get nervous. Tension is just a pulling force that's acted by a rope, cord, or string, and we've seen tension before. You just didn't realize that it was tension. For example, we looked at an inclined plane problem with a block on it that had a string attached to a pulley. And there was actually tension in that string, and we just called it an applied force. So tension is just another force that happens to be acting on like a rope, a cord, or a string, rather than a push or pull by another object. And so if you look at the diagram here at the bottom, we can actually solve for the tension in this string. We know that in this picture we've got a 1 kilogram object that is hanging, supported by that one string, and we know that if that string were not there, gravity would be pulling it down. So we still have an FW acting straight down, and we know that FW is equal to mg, or in this case 1 times 10, or 10 newtons. Okay. Now, I know that that means that the tension in this string has to be equal and opposite of that. If it was less than that, that object, that 1 kilogram mass, would fall because gravity would be pulling harder. If the tension were more than that, the object would be moving up towards the ceiling or whatever that's anchored into. So we know that they have to be equal and opposite, pretty much just like what we talked about in previous lessons, where if we had a box sitting on the surface of a table, for example, we had the force of weight which acted straight down, but then we had the normal force which acted perpendicular to that contact surface. So you can see tension, it's really the same thing. It's just another force, but it's the force that we see in ropes, cords, or strings. So here's that diagram of that tug of war problem from the warm-up. And the thing to remember with tension, we can see they're both pulling with forces of 500 newtons in opposite directions, but tension can only be found when analyzing an individual object. And so when we look at it as an entire system, that's where one makes the mistake of thinking it's either 0 or 1,000 newtons, but we know that neither of those is true. But when we look at one object alone within the system, for example, if we would look at just the girl that's pulling on this rope, it's easy to see that that tension on the string is an internal force. And again, we know that internal forces are going to be equal and opposite. So if she's pulling with 500 newtons, that rope is pulling back on her with 500 newtons. Okay. And if we would look at the guy within this system, the same thing. He's pulling with 500 newtons, and so that means that the rope is pulling him back in that opposite direction with 500 newtons. If you remember from that Paul Hewitt video that we watched, it's not how hard you pull on the rope that determines who wins the tug of war. It's how hard your feet push on the ground. And so whoever's pushing against the ground hardest would win this battle. Okay, now tension gets a little bit more complicated as more strings are used. But if you think about it like this, if you were, let's say, climbing a tree and you were to hang from one of the branches, if you hang from just one arm, that one arm is going to experience more tension or more force because it has to support your entire body weight, as opposed to if you were hanging from both arms. Well, if you're hanging from both arms, your total body weight is going to be equally distributed in tension forces going the opposite direction between those two arms. And so two arms, we would divide that FW by 2. We can see the same thing in this diagram here. So again, we have our 1 kilogram mass, which we know is going to have an FW acting straight down. And FW is mg, or 10 newtons in this case again. And before, we just had one string. Now I know that total, we have to have an upward force that's equal to 10 newtons. But since I now have 2 strings, I divide that by 2, which tells me that the force of tension in each of these strings now is 10 divided by 2, or 5 newtons each. Okay, now these pulley systems are going to get a little bit more complicated. So let's take a look at the top one here. One thing you want to keep in mind is that the tension in this rope the whole way along here is going to be equal. In other words, the rope isn't going to experience more pull or more force at any one point of that rope. And so you're still going to look at the mass of the object hanging here, which is a 1 kilogram object. So it's still going to have an FW of 10 newtons. But now I have to decide how that tension is distributed in that rope. If you have a system with multiple pulleys that you see here, so 2 pulleys, okay, what you can do is just count the number of pulleys, which is going to give you the number of ropes that are considered supporting ropes. So there's 2 pulleys, and therefore these 2 ropes that I'm putting X's on here would be considered those support ropes. And so I take that 10 Newton force and divide it by the number of pulleys, or the number of support ropes, in this case 2, to give me a tension of 5 newtons on each of these ropes. So this one is 5 newtons and this one is 5 newtons. Now, as long as this system is not accelerating, I know that the F net is going to be 0, and so that means that that applied force that I'm holding on to this rope with right here has to be equal and opposite to that tension, so that would be 5 newtons as well. When you look at the bottom system that you now have a little bit more massive object. You have a 2 kilogram object, so we know in this case its FW is going to be 2 times 10, or 20 newtons. And again, if I'm solving for the tension in each of the ropes here, I have to remember that the tension all the way along this rope is going to be equal. And so I count my number of pulleys. I've got 1, 2, 3, 4, so 4 support ropes here, 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 here. And so I take that 20 newtons divided by 4, which again is going to give me a tension of 5 newtons in each of those portions of the string. So again, my F net is 0 in this system as well. We're going to assume that it's not accelerating, and so that tells me that that force right here, that I'm either holding on to that, or it could be maybe anchored into a wall, but that force is going to be equal to the individual tensions that we just calculated, so that's equal to 5 newtons as well, so that we get that F net of 0.